Hi everyone, I'm gonna talk about single sideband modulation, SSB modulation. First of all, I should talk about double sideband modulation. For DSB modulation, you have message signal xt multiplied by carrier frequency AC cosinus 2 pi fct. This is transmitted signal for DSB modulation. XCT equals to AC xt cosinus 2 pi fct. Let's see what we will have in the frequency domain. Assume our message have this spectrum minus W to W. This is the message spectrum. The bandwidth of our message is W. For example, 5 kHz, 10 kHz, or 15 kHz in FM modulation. In AM modulation, they mostly use 3 to 5 kHz for voice. And now the spectrum of our DSB signal, I mean the Fourier transform of this signal, is we have frequency shift. We have spectrum FC, FC minus W, FC plus W, and we have the same in negative frequency. All things must be symmetric because signals are real. So here is minus FC and the amplitude is AC over 2. The bandwidth here is 2W. SSB, in SSB modulation we want to use W, the minimum bandwidth, and the bandwidth equals to the message signal. Actually a half of bandwidth of the double sideband modulation. What is the idea behind single sideband modulation? As you see, these two sideband are symmetric, so I can use this sideband and this one. We call it USSB, or I can only use this one and this one. We call it LSSB. There are two scenarios, two methods to have single sideband modulation. One is upper single sideband and other is lower single sideband. There is no major difference between LSSB and USSB. They are actually the same. Let's continue with USSB signal. We have DSB xt multiplied by carrier AC cosinus 2 pi fct. Then we use a filter to separate sidebands. We call it SSB filter. And at the output we have USSB signal. I mean, for example, this is the spectrum of DSB. In frequency domain, U multiply by frequency response. So assume frequency response, this red font. You can remove this sideband and hold this one, and here also you can have this and remove this one by using this filter. So by filtering we can have SSB spectrum. Minus FC, minus FC, minus W. Here is AC over 2. This is the spectrum of USSB signal. And as you see, bandwidth here is W. Bandwidth is W. In analog modulations, SSB is a bandwidth efficient modulation. Now I'm gonna continue to find the tricky part of this discussion. XCT. How can I find time domain signal of USSB signal? How can I find it? We have this and we have to do inverse Fourier transform. Before start to finding the time domain SSB signal, I should introduce Hilbert transform. Hilbert transform. Hilbert is a LTI system with a specific frequency response HQF. The output, we call it X hat equals to Hilbert transform. It is Hilbert transform of XC. HQF equals to minus J sine F. It means the absolute, the magnitude spectrum is 1. We only phase shift for positive frequencies and negative frequencies, minus 90 degree and plus 90 degree. This is the Hilbert transform, and in time domain the convolution is X hat t equals to minus infinity plus infinity x tau pi over t minus tau dr tau. This is Hilbert transform, and I'm gonna use it for single sideband modulation. To find time domain waveform, I bring a spectrum to the baseband. To go to the baseband, you should remove this one and shift this one with FC to the left. So the low pass equivalent of USSB signal is this W0 AC over 2. This is X low pass F. And I should build this based on the message spectrum. I should relate this to this one. How can I do this? By using Hilbert transform. Let's compute Hilbert transform of this spectrum. It is X hat F. For F positive, I can multiply by minus J. And for negative frequency, I multiply by plus J. We have this. I want this. I can multiply this one by J. If I multiply by J, what we will have? J multiplied by minus J is 1. 1 plus 1 is 2. J multiplied by J minus 1 with 1 added by 1 is 0. So this sideband is removed. But the amplitude for this one is 2. So I can write X low pass F equals to AC over 2 XF plus J X hat F over 2. And now I can take inverse Fourier transform. X low pass T equals to AC over 2 X T plus J X hat T. The final part is bring this low pass to the band pass, convert it to the band pass signal. Let's continue. What is the relation between band pass and low pass equivalent? It is 2 real part X low pass T E J 2 pi FC T. If I substitute X low pass T, we will have XC T equals to AC over 2 real part xt plus j x hat t multiply by, I can, using Euler, cosine 2 pi fct plus j sine 2 pi fct. We can multiply this term by this term and we have 4 terms, but only 2 terms are real. We have here real part. Finally, we will have AC over 2 xt cosine 2 pi fct minus x hat AC over 2 x hat sine 2 pi fct. This is the USSB signal. For LSSB, if you repeat the repeat the stages, you only have plus here instead of minus. In LSSB, you have plus here. We reached to the end of this video. I hope you enjoyed. Thank you for watching this video.